to the last presentation of today. This presentation will be conducted by Dr. Pedro Melo, that is a full professor at University of Trás-os-Montes e Alto Douro in Portugal. And the presentation that he will give to us, it's entitled Towards Robust Supervised Models for Grape Ripeness Assessment. So I give the floor to Dr. Pedro Melo. So whenever you want, you're free to.
Good morning, everybody. I hope you're listening correctly. I'll try to share my presentation, but not yet available. Thank you, Albert, for your kind introduction and kind invitation for me to being here. It's a pleasure to be presenting our work at the first TERRATECH Workshop. While I'm not still able to share my presentation, I don't know why.
Nobody is using.
I don't think I can. Okay. No, yes. I hope you are now looking at it. Yeah.
Right now. Yeah. Right now.
Okay. Thanks very much.
Thank you.
My presentation is much more focused than the three previous ones. I'm really talking about a specific case of application of technology in agriculture. It's grape ripeness assessment, mainly for wine production, but can be the technique can be applied to different fruits and other crops as well. Let me just check. Yeah, so we are a small team from Universidade de Trás-os-Montes and Alto Douro in Portugal, in the northern part of Portugal. I'm Pedro Melo Pinto. I lead this small team, and we have a couple of collaborations besides the team we are presenting here. We work at UTAD, which is the Center for the Research and Technology of Agro, Environmental and Biological Sciences here at UTAD. And we've been doing research on grape and technology and the application of technology in grape production for several years. But as I told, we will try to focus here on the grape ripening assessment. The outline is more or less like this. So first we start with the introduction of the problem and several other issues that are relevant to the problem. We have an early machine learning based model that it's the basis for all the work we've been doing. We will address the feature selection because these models tend to be with many parameters involved, so feature selection would be nice and easy for faster and reliable solutions, but as we're going to see, it's not always possible. Then we have evolved the early machine learning model to a deep learning model, and I'm presenting that. It's the most recent one we have developed. Several of, I guess, the previous speakers already addressed the problem of when we use artificial intelligence. Most of the time we need to explain that what the models are really doing, and that's not clear from the model itself. So I'll try to address a little bit of that, and I will end up with some conclusions and future work that we can address and we'll try to address. I'm going to try to be fast here because I guess all the previous speakers already addressed these issues. So there's a boom of the use of artificial intelligence, I would say everywhere, but in the case that we are dealing here with in agricultural problems, or in general terms, there is a huge increase of using of deep learning and other artificial intelligence solutions to let's say, many problems. This is kind of wishful thinking that we can have about agriculture. So today, I would say we are still in the middle part of this graphical depiction of what agriculture is and what can it be. We are still dealing with many data and with not so much solutions for that data. That can be confusing for the producers, for the farmers, for the producers, for everybody involved in agriculture. So I hope we can go into the future, probably you are already in mid-future now, where this information can all be gathered up and bring up good technical solutions for most of the problems. This means that we are entering a new, let's say, age of agriculture that we can call agricultural 4.0 or precision agriculture, but it all, in spite of the name we can use, it's all based on digital aspects that were not usual in agriculture. Now starting to focus on the problem of grapes and of ripening assessment of grapes. Precision agriculture in using data, well, massive data, has been mainly dealing with 2 or 3 aspects, that spatial referencing, monitoring, and mapping. That's what we've been talking about or heard about in the previous speakers' presentations, and of course decision support systems and differential action. But I'm more focused on what you can do with the data than what the actions you can take after you get information from the data. So monitoring from this point of view it will play a very pivotal role in all of these. And so we try to come up with a solution for grape ripening assessment. Why? Because Portugal, in the area where my university stands, is very strong on wine production, and wine production is also entering a new age, let's say, like that, because wine quality is of paramount importance. And wine quality depends on grape quality, and the grape quality, of course, has to be monitored to be pushed to the limits, let's say, like that. So harvesting at the optimal point would be very, 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 very important, and the selection of the grapes according to, let's say, specific tasks for specific wines or quality features would be very interesting as well. This would have, or this will have, a strong impact in the winemaking process, and of course it represents, let's say, a cutting-edge solution for the winemaking sector. What we're trying to do is that we have the input data either from lab or from field. We try to come up with a model, and with that model we have a prediction on the quality of the, well, not the quality of the grape, but more on parameters involved in ripening of the grape. So what we're trying to assess, and we'll come to that later, is that what values of sugar contents, acidity, and anthocyanin are expected to have in that grape. And the thing is that we do that without touching the grape. So we collect an image, as Matthew has presented before for nitrogen. We collect the images with an hyperspectral camera, so we don't touch the grape, and we end up with a value for, that's the case where I'm going to present for sugar contents on the grape. And that would be very, very important to get, because if we get that, we can put that on a robot arm, for instance, or a robot in the field, as the ones presented by Manuel Silva, and we can have a, let's say, a 24-hour monitoring process available for getting sugar contents on the grapes, which is very different from the process that it's done nowadays. Nowadays, the process is by, let's say, traditional laboratory measurements. So it's based on chemical. It's expensive, it's destructive. You have to get the grapes, take the grapes and things like that. It's time consuming and it's not very friendly for the environment, because it uses chemicals, of course. So this methodology we are still developing, that we already developed, is non-destructive, and it can be fast, and it can avoid all the lab work that is done today. And we use, as I told, hyperspectral imaging. So we have information from the visible part of the spectrum, as well as the near infrared part of the spectrum. And we use artificial intelligence to come up with the results for sugar content estimation, or for pH, or for anthocyanin concentration. And this model has two time phase steps, let's say. One, when you validate the model, and this involves a learning phase, which is time consuming, but you only do it once, hopefully. And it's not in real time. Let's say we can do it previously. And the second part, where the user uses the model, and this is called the testing, where we can process any sample in a question of seconds, including all the process. So this is very fast. Sorry. This is very fast, and it does not involve any of the traditional lab works that it's necessary today. The problem is that grapes, unlike other fruits or crops, is very variable, because there are many varieties. I guess only in Portugal we have more than 300, and we have other aspects that can influence greatly, let's say, the maturation and the process of maturation of the grape, such as climate, terroir, sun exposition, and kind of different factors. And this represents a challenge when you try to develop regression methodologies, that what we're trying to do, because you might end up with a methodology that works well for this kind of, for us, one variety of grapes, for one particular producer, because he has this field or the vineyards in this position. But when you change variety or the position of the vineyards, you don't get the same results, because the data is so variable that it may not be, let's say, fit to use the same model to different kind of data. This is what in regression, in the models we're using, we call the generalization problem, and we will address that later as well. Why we use hyperspectral imaging? I don't think Matthew has addressed this aspect, because hyperspectral imaging, it works on near infrared, and images are based on light reflection on the surfaces. So when you have near infrared, which are stronger or higher wavelengths, you have you achieve a small light penetration under the skin of the grape. And depending on the authors, that light penetration can go up to, let's say, 1, 2, 3 millimeters, which allows us to get information from the light reflected that is not from the outside aspects of the grape, let's say the skin, but from the under the skin aspects, which are the chemical exchanges and transformations that are happening because of the grape ripening. Besides that, hyperspectral imaging is very fast and it's not destructive. So it all end up with a very interesting technology to do the work we were supposed to do, or we are trying to develop. Spectroscopy, more generally speaking, has been used for many aspects in agriculture, and in grapes as well. Less than in other crops, but nevertheless with some extent. But mostly it addresses quality parameters, uses different type of samples, grapes, bunches, skin, seeds, homogenates. So it covers a very wide spread of inputs. From the technical point of view, it used to use techniques such as partialist squares and sport vector machines and artificial neural networks. But recently, there's an increase on the use of deep learning, let's say more robust methods such as deep learning in different aspects of grapes and visual inspection, quality assessment. Prediction is not prediction of the parameters is not. There are some work, but is not as developed as other aspects of grape assessment, like visual inspection, pest inspection. But nevertheless, there is some works. Because the process of ripening is so complex, it will be difficult to come up with an analytical solution. So from my point of view, these kind of methods, such as supervised statistical-based methods, are the nowadays solution for the problem. So using deep learning or other kind of machine learning approaches would be, from our point of view, the natural solution for the ripening assessment of grapes. But because of the variability of the data, this generalization aspect of the models is really need to be studied, and that is not found in many papers in literature. So we're trying to address that as well. Our early model was based on this is our experimental setup. As you can see, there's the camera over here, and on the vertical axis from the camera you can spot 3 grapes on white reflection base. So that was our experimental setup. From the beginning, as you can see, this is not a dark room, as usually when you do imaging, you perform that on a dark room to avoid any influence from the natural light into the artificial lighting system. We didn't do that because we knew that these kind of systems could only be helpful if we can transfer them from the lab to the field. So let the system learn from the beginning. We have, of course, control conditions here because we have artificial light, but introducing natural light on the system already, let's say, get us midway from lab to the field experiments. What we do is we using, this is more, let's say, technical. I will try to go fast on this. We just read one line on the grape, trying to read the equator line, and for that line we have around 1,000 pixels, so units, and for each unit we have information for 1,000 channels. Just to compare with normal photo, so when you take a photo, you have 3 channels, the blue, the red, and the green. We have 1,000 channels here, so it's much more information for the same kind of image. This is actually the images we get. So the berries are marked on the image. So we have on the vertical axis is the different information for the different wavelength of the light reflection. We did the sampling carefully. So from the same vineyard, we have 3 different regions associated with different vigor. That were chosen by our industrial partner, by the way, is Symington Estates from Portugal. And we chose different locations for the same region for taking into account the sun exposition. So we try to diverse the sampling as much as we can. One sample for us is either 6 or 12 berries up to 2017, if I'm not mistaken. We use 6 berries, but then because we had problems to getting the referential data, which is the data we are based on to train our models, we changed the one sample to 12 berries. It's no really importance on the model, but we perform 2 berry rotations. So every time we take a sample, we have 2 berry rotations, which gives you 3 images per berry. And because of noise, we take 32 images at one time from each grape. So at the end, you get about 600 images for one sample, or 1,200 images for one sample if you have 2 grape samples. 12 grape samples, which is a lot of data, and it's very complex data to analyze. We acquire the images on fresh grapes, so we take about 20 minutes from grape collection to image performance. We froze the grapes, and then we turned the grapes before performing the lab measurements for the reference values of sugar contents, in this case of pH or anthocyanic. Our general model is like this. So far, we have used 4 different machine learning or chemometric approaches. The chemometric, more traditional one, is PLS regression. The machine learning has been the original artificial neural networks model. We also try support vector machines and deep learning. This is the reflectance we got, as you can see on the left downside. This is the example of the normalized reflectance spectra. And as you can see, they all follow a kind of trend, but you cannot really get any, let's say, visual values that really stand out. And this is only for one variety and from one day. If you change varieties or if you change days, the change of the spectrum will be much more different than this. So we employed machine learning, so artificial intelligence models. We have the train and model validation, and then we test. We always spare some samples from the model training and validation to use for testing. So it's independent testing to see if the model generalizes correctly. And from let's say in 5 years, in the first part of 2010 to 2015, we tried to prove the feasibility of the methodology. These are the results we got then, either by chemometric methods or by neural networks or support vector machines, and they were pretty good. Industry, the industry threshold, for instance, for the error on sugar contents would be about 0.5 degrees Brix. So we were pretty close on test sets using support vector machines, for instance. The problem here is that we only used one vintage of one variety, either for testing or for training or for testing. And that can be really a problem, because you don't want a model that only works with one variety. In this case, were a Portuguese variety called Touriga Franca. And you want the model to work no matter the variety you're using, and no matter the country, the sonic exposition, the climate. So that would be a different challenge from this more simple one. We also tried to see or to look into the wavelengths we are using. We have a lot of wavelengths, around 1,000. So probably not all the wavelengths are significant for the problem. We use different methods for feature selection, either linear or non-linear, but no really wavelengths stand out from this analysis. For instance, we use these 5 methods, mostly linear, with Touriga Franca from 2012 vintage. And of course, cars, which is a very popular feature selection method from the literature, we can get 0.7 error on the same data we've seen before. So it's even better than before. And we say, well, wow, we got here a solution. You only have 63 wavelengths, so much less than 1,000, the original 1,000, and we got better results, so we found it. But no, the problem is that when you change the test data from one variety to another, from Touriga Franca to Tinta Barroca in this case, which is another Portuguese variety used in port wine, for instance, and we changed the vintage from 2012 to 2013, the errors, well, went skyrocketing. So the errors from the 0.7 using cars, then changed for 4 or over 4 or over 5, which were errors that are not really admissible for this kind of work. So the problem in prediction of parameters here for grapes with such variability is really the generalization problem. We also tried the other methods, non-linear, more, let's say, more strong ones, and with no really good results at all. And even training, well, have test sets with different vintages to see if the problem of the using only one vintage would be interfering with the feature selection. But no really standout wavelengths can allows us to have a feature extraction and a reduction, a complexity reduction of the problem. So we changed the model. We instead of using the artificial neural network or support vector machine, which were already very good models, we changed for deep learning models, which are even more, they can extract more information from the same data. This is the variety of the data we have. So in green is it's Touriga Franca, in yellow is Touriga Nacional, and in blue, light blue, cyan is Tinta Barroca, which are 3 of the most important varieties for port wine. And as you can see, they are very variable. They really vary a lot. So that's the problem we get. Up to now we have a little bit more now. We have 2,700 samples, which is very good for this line of work. We end up collecting samples in 2018 because from then on we have the pandemic. And we changed from the neural networks, the traditional one, to deep learning, what we call iGrapeNet. We have some kind of pre-processing, we can skip that. We have training as before, and we have testing as before. The difference is the training is done with a different model, this one. This is a one-dimensional convolutional, deep learning network with feature learning, feature extraction with one dimension only, and with fixed size of kernel size, number of channels, number of dropout, whatever. It's all fixed. And with this architecture, we can evolve from the previous results to much better results, as you can see. The most difficult case was the last one. We trained the network with all the data from Torriga Franca we got, so from vintage 2012 to 2018, and we test it with any kind of data from Torriga Franca, and we got an error about, let's say, 1.20, which is much better than we had before. Let me remind that these kind of errors were using the same tiny data set for training and for testing. And here we have a huge data set, and so the model has to be much more adaptable to new data than this one over here in the first place. Even so, we are not happy with the results. And so we improved the method. And what we did is that we let the method learn, the model learn everything, every aspect. So we optimized all the values of, let's say, number of channels, kernel size, number of percentage of dropout, number of neurons in the fully connected network. So we optimized all with the Gaussian process, and we tried 3 different pre-processings. The best one is CH, so Sabit-Sequale, and with that we have these results. These are our let's say most recent results. So we trained the network with all the Torriga Franca samples we have, but we test it not only with Torriga Franca, but with all the different varieties we got. And even if we change varieties, we have a lower error than previously, which is around 1.1. We already got slightly better results than these with the optimization of the model. And the previous example that I gave, so this one, which were 1.20, the error, now with the new architecture, we got around 0.76 okay. So we are very, very close to the threshold that the industry needs for getting, let's say, satisfactory input from these methodologies. What we tried later was to explain the model. So it's normal to say that artificial intelligence are black boxes nowadays. So we tried to look into a little bit of these black boxes. There are several methods for doing that, but all those methods are trying to overcome a kind of difficulty that the users tend to have with artificial intelligence. If you don't understand the model, you tend not to trust the model. So we try to overcome that. We used what is called visualization methods post-hoc, so after the results. We use 2 techniques, occlusion and backpropagation cams. The occlusion is easy to understand. So if you have an image and you want to know if it's a cat or if it's a bicycle, or if it's another cat, or no, the first one is a door. What you do is you part of the image and see if the response is less important than used to be. And the much less important the response would be, the most important that area, specific area on the image as to the final result. We do that with grapes, and the results were like this with the spectra. We removed specific wavelengths, and we tried to see if the error has increased a lot compared to using all the wavelengths. As you can see, no really range of wavelengths removed stand out in this process. The other way of getting some kind of interpretation of what's going on, it's called class activation maps. It's based on a property of the networks itself. It's on backpropagation process of learning in the networks itself. And using that, we got these results. This is a 5 random spectra I chose from the results we got. And with that method, now we have something. We tend to have these 4 or 5 areas of wavelengths that are important. So this is what we are now doing, is using only these wavelengths, trying to come up with models as strong as the previous one I show you. And if we got that, we have paved the way for much more cheaper solutions of cameras, of course, dealing with much lesser information with the same results. That would be very, 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 very good. So that's the conclusion we have, is that the model is feasible. The results with deep learning are very, very, very promising, very interesting nowadays. The problem is that we need a lot of data. We have about let's say, around 3,000 samples, and the double or 3 times would be even better, of course, even if you used a solution called data augmentation. And we are now testing the infill data we have already got. We are trying to decide if the best solution would be a single model fits all, or different model calibration for different families of varieties would be better. We are, of course, trying new architectures that are appearing every day here. We are paying special attention to the so-called attention models. And there's a new thing that might be very, very interesting to use here, is self-learning, so models that learn from themselves, which would provide us to override the need of such amounts of data that are almost impossible to get. And finally, we try to expand these explainability things of the networks, which are very, very important for the producers, for the end users to trust on the technology. I think that's all. I think I'm on time or less. Thanks for your attention. Of course, I'm open to any questions you want to present.
Thank you very much for your clear presentation. So, as Professor Melo has said, if anyone has any question.
Okay, I'm not sure if it's really a question from Rose Pereira. Yes, it seems that there is a long way before using these solutions. Yes, Symington already used some of them, let's say, experimentally, or but yes, the problem probably here is more on the cost of the solution than on the technical side of it. The cost of solution nowadays is around 25,000 with the cameras and everything. So it can be quite expensive, but probably in, let's say, 1-2 years, there are probably cheaper solutions for this problem. If you're trying to use it on a vineyard, we tried with a team from Politécnica de Valencia, Francisco Viramar, and with people from La Rioja, and it's promising. I mean, I think we are not in midway. We are past midway of a solution that can be with the industrial or production, or let's say industrial use for the end user.
Thank you very much. Yeah, I would say that these are very good news for the community.
Hopefully.
So any other question to Professor Melo? So again, thank you for accepting our invitation to be a keynote speaker in our workshop, our first workshop. And thank you very much for this nice presentation.
Thank you. Thank you for having me.
So with this last presentation, we close this first session. So we will take a break, brief lunch break. So we'll have more or less 1 hour and a half. We will meet again in here at 2 p.m. European Southern Time. So see you in a while.